Right. So today is 18th of April. Um, since we were away for quite some time, I'd like to uh, say something about Fourier transforms. If you recall, the Fourier transform is a transformation from a time domain signal to a frequency domain signal. So the definition of the Fourier transform is the Fourier transform of a signal, time signal xt, right, is the integral that goes from minus infinity to infinity. The integrand is a product between the time signal itself and the complex exponential e to the minus j omega t dt. Okay, this is the definition of the Fourier transform. And since this is a function of the frequency omega, omega here is the frequency, it's the angular frequency, the unit of omega is radians per second. And when we integrate it and plug in the boundary conditions, the time variable t will be gone and we will be left only with the variable omega. So the whole integral is a function of omega. That's why we will denote it by a big function x now of omega. So it is this integral is just a transformation from the time domain signal xt into a frequency domain signal x omega. And the transformation here is a one-to-one transformation, meaning that if we know xt, we will uniquely identify, we will uniquely determine x of omega and vice versa. Okay, so that means if you take the Fourier transform of the inverse Fourier transform of x of omega, okay, we will get x of omega back uniquely, right? On the other hand, if you take the inverse Fourier transform of the Fourier transform of x of t, we will also get x of t back. This is what I meant by unique transformation. And we now know a couple of time domain signals that we now know the Fourier transform of a couple of time domain signals. For example, the unit impulse signal has the Fourier transform pair of 1, all right, and the constant signal 1 has a Fourier transform pair of 2 pi of delta. Okay, and the rectangular pulse signal of width t. Okay, with t, I mean this notation means the signal, the rectangular pulse signal that goes from minus t over 2 to t over 2. In other words, the width of this signal is t. Okay, this is called the rectangular pulse signal, and the corresponding Fourier transform of this signal is t sinc of omega t over 2. Also, we also know that the cosine signal of frequency omega 0 has the Fourier transform of pi delta omega minus omega 0 plus delta omega plus omega 0. So the spectrum of a cosine signal is a pair of impulses Okay, one is at omega 0 and the other is at minus omega 0. So that will indicate the frequency that those impulses indicate that the cosine signal has a frequencies at omega 0 and minus omega 0. Okay, and we also know a couple of properties of Fourier transform pairs, notably the linearity, the time shift, um, the convolution, um, multiplication by complex exponential. On those properties have been discussed already, so I'm not going to repeat it. Um, and the last property that we talked about last time, I think, was time multiplication. So I'd like to take a few seconds talking about it again. Excuse me. It is number 8, so I'd like to make it consistent. Number 8, it was time multiplication property. Okay, time multiplication property that it goes like this. If we multiply two time signals together, okay, the product of two time signals, and we take the Fourier transform of it, the result would be the 1 over 2 pi, which is a constant, multiplied by the convolution integral between x of omega and y of omega. Um, so this is the time multiplication. If you recall the convolution property, so recall the convolution, time convolution property. The time convolution property states that if we do the time convolution integral between two time signal and we take the Fourier transform, the result will be the product of the Fourier transform of their Fourier transforms. So when you look at this, you see the similarity between these two properties. In other words, for Fourier transforms, uh, if one domain is a product of two signals, the other domain would be the convolution of the transform of two signals. For example, if in the time domain we multiply two signals together, then the in frequency domain we do the time convolution together. On the other hand, if the time domain is time convolution, then the other domain would be the multiplication. So you see the similarities between them. In fact, these are consistent with duality. Okay, so if you apply the duality property on this property, you see that the left hand, the top left, will go across to the lower right corner, and the top right will go across to the left to here, replacing omega with t and replacing t with omega. So you see this is inconsistent with um, a duality property. But but this is just a note here that I'd like you to notice the similarities in these properties. As an example, this example is called modulation. Suppose we have a signal m and we multiply the signal m by a cosine function, by a sinusoidal function, and we call this product signal x. Okay. If you are into communication, you will see this type of multiplication a lot. This multiplication or this type of product is called modulation. This is called uh, this is called a modulation between MT and the sinusoidal at frequency omega 0. This is a modulation. Now, we'd like to know uh, the frequency spectrum of xt. In other words, we'd like to know if we do the modulation between two signals, what would be the resulting frequency spectrum. So to answer that, we need to take the Fourier transform of this equation, okay, on both sides. If you take the Fourier transform of both sides, then the left-hand side would be the spectrum of x, okay, and the right-hand side would be the Fourier transform of mt, which is a time signal, an arbitrary time signal, multiplied by cosine of omega 0 t. Now we can use the time multiplication property here, okay, where x here is the signal m and y here is the cosine signal here. So we multiply them, okay, and then we take the Fourier transform. That means that the right hand side will be 1 over 2 pi, the spectrum of m convoluted with the spectrum of cosine. So let's write that down. So it's going to be 1 over 2 pi, the spectrum of m, which we call m of omega, and convoluted with a spectrum of cosine. And what is the spectrum of cosine? It is pi, right? It is pi, and then delta omega minus omega 0 plus delta omega plus omega 0. Okay, this thing here that I wrote down is just the spectrum of cosine, which you can find in the table, right? This can be found in the table. So we do the convolution. If you do the convolution, we can take the pi factor out because convolution is a linear operation. So when we take the pi out, then we have only 1 over 2. And because we know from the distribution property of convolution, we can take the m inside to the curl parentheses, right? So we have m of omega convolved with delta at omega 0 and plus m of omega convolved with delta at minus omega 0. Okay, this equation comes from the distribution property of convolution. It's just like when you multiply two things together and the other thing is a summation of some things. So you can take the product inside of the parentheses. So what is this convolution? We know that if you want to, what is this convolution? We know that if you convolve something with the delta, then we're going to get that something back because delta is the identity of convolution, right? But if you convolve something with delta that is shifted by a constant omega naught, then we're going to get that something back. But now that something has to be shifted as well to this position, right here. So here, if I'm not sure if you can recall this, you convolve this function with delta shifted to this position, then you're going to get what you're going to get is you're going to get the same m back, but shifted to position omega 0 as well. Okay, this is from the property of convolution, and same goes for this as well. This is convolved, m omega is convolved with delta shifted to the position minus omega 0. So the result will be the function m shifted as well to the position at minus omega 0. So we have m omega plus omega 0. So this is this is the frequency spectrum of the signal mt modulated with sinusoidal at frequency omega 0. So let's plot this. Okay, let's try to plot this. Suppose that the signal m looks like this. Let's suppose the signal m looks like a triangular shape here, where we have omega m here and minus omega m here. Let's call this m of omega. Let's call this 1. Now, if we modulate this function with cosine at omega 0, then the resultant spectrum will be this spectrum shifted to the right and shifted to the left. You kind of like, you halve it, you take half of it and shift it to the right, and the other half shifted to the left. Yeah, let me write it down for you so that you can see. Yeah, look at this. I'm gonna copy this. Okay, I'm gonna copy this, and then I'm gonna paste it, and then I'm gonna erase this. And what I'm gonna do is I'm gonna have to resize it. Okay, see, I'm gonna resize it to half of it. I'm gonna resize it. No, I can't. I can't. Sorry, I can't. I can't do that. I can't do that. Because if I resize it, the whole thing, then the horizontal will be resized, which I don't want it to be resized horizontally. So when you do the modulation, the resultant signal will be half the height of the original spectrum, but move to the left and move to the right here. Here. Okay, see this one is this guy shifted to the left. Okay, and this one is this guy shifted to the right. But then we have to make it half the height, and then shift it to the right and to the left. So if we try to mark down the horizontal axis, okay, this would be omega 0, and this would be minus omega 0. See, the signal m, right? You take half of it, right? And then you shift it to the right. Shift it to the right means you shift it to omega 0. Center, it was centered at 0 before, right? And then you shift it so that the center would now be at omega 0. Shift it to the right. And then this would be omega 0 plus omega m. This would be omega 0 minus omega m. Okay, and this one as well, this one would be minus omega 0 plus omega m. And this is minus omega 0 minus omega m. And of course, the height here would be 1/2 of the original height. And this would be the signal x, which is mt modulated with cosine. So you see, the modulation process, the modulation operation In time domain, it's just the product between the signal with a sinusoidal signal. But in the frequency signal, it's like you shift the signal spectrum, the spectrum of the signal, to the frequency that you are modulating the signal with. Okay, so modulation means frequency shifting. All right, frequency shifting, and this is very useful operation in especially in communication where you have to modulate signals, where you have to shift the frequency of the signal uh, to to make it position at a higher frequency. All right, so you can transmit it using electromagnetic radiation. Okay, all right, okay, all right. Any questions, please? No. All right, so we're done with properties of Fourier transform. So uh, the next topic would be spectrums of some signals. One is of course the DC signal. So what are DC signals? DC signals are just constants. Okay, so in other words, these are constant. So we know that if you take the Fourier transform of 1, the result would be 2 pi of delta omega. So the DC signal has a frequency presence only at omega 0, at 0 frequency. So this means that DC signals only have okay, you cannot find the presence of DC signals in other frequencies other than at 0 hertz. So that's DC signals. Second is unit impulse. The unit impulse is delta, right? And we know that if you take the Fourier transform of delta, you get 1. So that means that the delta signal, the unit impulse signals, has a frequency, has its presence across all the frequency range. If you think about the delta as a strike of lightning, so every time there's a lightning strike, it means that it can send interference across all the frequency spectrum. This is what this one implies. So if we think of a unit impulse as a lightning strike. Okay, a lightning strike is something very, very large in amplitude, right? But very, very short in time. So it's like boom, and everything is fried because the energy is so large. But the amount of time, the duration of a lightning strike is so small. So you can imagine a lightning strike as a unit impulse. So every time when there is a lightning strike, you see that a lightning strike, because the Fourier transform is 1, so it is equal to 1 across all the frequencies. Okay, so it can send interference across all the frequencies. That means that every time when there's a lightning strike, you have noises across all the frequencies, and these noises can go to your electrical appliances and interfere with your signals at every frequency. Okay. Then every time a lightning occurs, you will have interference across all frequency spectrum. Okay, so that is not good, right? The third is a unit step signal. So unit step signal is UT, right? And everybody loves UT. Everybody knows UT. And what we do know about UT is it goes from 0, okay, to 1 at time 0. This is UT, right? UT. And it turns out that we can write down UT as 1/2 of 1 plus the signal. Now, if you make an attempt to find the Fourier transform of that UT directly using the integral definition, then you will be in trouble because this integral will not converge. Okay, and every time something is not converged, you know that the integral will have to be written as a function of delta. There will be a delta function coming up. Okay, when the integral is not converged. So in this case, it doesn't converge, right? So we do not want to deal with the direct integration of the Fourier transform. So that's why I have to bring the signal up here as a tool to help us find the Fourier transform of UT. So if you write UT as this representation, and I'm not sure if you can recall the signal. The signal is a signal that goes from -1 to 1. This is a signal that we talked about some time back. This is signal. This is UT. So you see that you can write down if you multiply half of it, if you multiply 1/2 to the signal, then it would be going from -1/2 to 1/2, right? And then you shift it 1/2 up. You're gonna get UT. Okay, that's why we have this formula here. Now we take the Fourier transform on both sides. We're gonna get UT as a Fourier transform pair of 1/2. Now the Fourier transform of 1, what is the Fourier transform of 1? It would be 2 pi delta, right? That we know already, the Fourier transform of 1. And the Fourier transform of signal, I think we have found it already, that would be 2 over j omega. Okay. So you take 1/2 inside of the parentheses, you're gonna get pi delta, okay, plus 1 over j omega. So this is the Fourier transform pair of the unit impulse. I'm sorry, of the unit step. The term delta is present here because the average value of u is not 0. See, the average value of u is not 0, so there is a DC signal present in u. You see the DC signal here? The average value is not 0, right? That's why we have delta here that represents the average value. Okay, and 1 over j omega here is that this one comes from the shift, the jump, okay, from 0 to 1 here. right? This is what this one represents. The next signal would be switched cosine. So what is a switched cosine? The switched cosine is defined as a unit step signal multiplied by cosine. So it's kind of like a sinusoidal signal that is switched on at time zero. Okay, so if you try to plot this signal with respect to time, what we get is we're going to get a cosine signal, but now it has to start at time zero. Okay, so we're going to get a cosine function starting at time zero here. And when time is less than zero, it is zero. So this is why it's called a switched cosine. It's switched on at time zero. It's like you have a switch, right? And you turn it on at time zero. So the sinusoidal will come out at time zero. And this is T naught, which is the period of it. And this is 1, this is minus 1, this is x of t. And let's try to find the Fourier transform of it. Let's try to find the spectrum of this switched cosine. Now we take the Fourier transform of both sides, right? On the left hand side, it will get x of omega, and on the right hand side, it is a multiplication between u and cosine. So we can use the modulation property that I talked about in the previous example. So this is if you look at this is just a modulation, right? Modulation between u and cosine. So when we do modulation, we have 1/2 of the Fourier transform of u shifted to the right and shifted to the left, right? So we have this. This is from an example that I talked about last time. If you remember, in the last example, in the previous example, I used notation m, right? But now it is u, it is a function u, so I replaced m with u here. Now, what is the spectrum of u? The Fourier transform u is given by this, right? Okay, so what we do is just we replace omega in this with omega minus omega 0 and plug it in here. And for this, okay, and for this one, we replace omega here with omega plus omega 0 and plug it in here. So I'm gonna have 1/2 of pi delta omega minus omega 0, okay, and plus 1 over j omega minus omega 0, and this is this guy, okay. The whole thing here is this guy, which is the first, which is the spectrum of u replacing omega with omega minus omega 0. And we have to do the same for the right one here, the other one, but now this time we have to replace it with omega plus omega 0. Here, okay. And now you can group them together. Excuse me. Okay. All right. You can group them together to have a pi over 2 Excuse me. Let me make sure something. Yeah. Okay. Pi over 2 of delta minus omega 0 plus delta omega plus omega 0. Okay, and the rest would be 1 over j omega minus omega 0 and omega plus omega 0, right? Because you have to add these two together. Okay, when you add these two together, then the denominator will be this polynomial, and as for the numerator, it would be j omega plus j omega 0 plus j omega minus j omega 0. Of course, multiplied by 1/2. All right, and then you see that the j omega 0 will be gone. Actually, we don't have j here, right? So it will have pi over 2, and then we just copy this one down below. Save time here. Okay, and then the right hand side would be omega squared. I'm sorry, not omega squared, just omega, just j omega. And then the denominator would be omega squared minus omega naught squared plus. So this is the frequency spectrum of the switched cosine. You see, this is the spectrum of cosine, right? This is spectrum of cosine, and then you have to add this little thing here because this is a result from the switch process. Okay, this is a result from the unit step function. Number 5, pulse cosine. So what do I mean by pulse cosine? Pulse cosine is defined as rectangular signal of width t modulated with cosine at frequency omega 0. So this is pulse cosine. So if you recall, this rectangular signal is a rectangular signal that goes from minus t over 2 to t over 2. So the width of the rectangular is t, but the width is t, right? Going from t over 2 minus t over 2 to t over 2. Then you multiply it by cosine. So in the time, if I were to plot the signal x versus time, then the shape of x would look like this rectangular, and then I have to have cosine inside. So this is a pulse cosine. This is a pulse cosine. The oscillation there is an oscillation inside a rectangular shape. So the rectangular shape goes from minus t over 2 to t over 2. Okay, this is controlled by the rectangular signal here. This rectangular tells us that the cosine has to go from minus t over 2 to t over 2. Okay, and the oscillation inside is given by the cosine here. So the frequency of the oscillation is given by omega 0. Okay, so oscillating at omega 0. Now we want to find the the spectrum of xt, right? Again, we're going to use the modulation property. So if you take the Fourier transform on both sides, the left hand side will be x of omega. The right hand side will be 1/2. Okay, I'm gonna call rectangular here as m, right? I'm gonna call it as m. So from an example that we did, the inside would be m omega minus omega 0 plus m omega plus omega 0, where m is rectangular. Now, what is m here? Where m omega is the Fourier transform of rectangular t over t, t over big T, right? But the Fourier transform of rectangular is the sinc function, right? So this is just t of sinc omega big T over 2. So m, big M, so big M is the sinc function, it's a sinc signal. So we have to plug in the sinc signal into our equation. But now we have to replace again, we have to replace omega with omega minus omega 0, and the other one replacing omega with omega plus omega 0. So we have the spectrum of the pulse cosine as 1/2. Actually, it has to be t here. T over 2, t half of t. The left one is sinc, replacing omega with omega minus omega 0 and t over 2. And the other one is sinc omega plus omega 0 t over 2. And now this is the spectrum of the pulse cosine. Okay, so let's plot this one. Let's plot this spectrum. Let's give it a try. Let's give it a try. We know that this is just sinc, right? This is just sinc shifted to the left and shifted to the right, and put them all on the same axis. So the first thing that you have to realize is what is the shape, what is the plot of a sinc signal. Okay, a sinc signal is just is kind of like a dying cosine, dying sine, right? So the sinc signal actually is this one. This is sinc, right? Let's call this sinc. Let's call this t sinc omega t over 2. Okay, so this is this is 2 pi over t. This is minus 2 pi over t. Now, we know that we have to shift it to the left and shift it to the right, right? But we have to take half of it. We have to half it first. So half of it shifted to the right would be 1, 2, 3, 4, 5, 1, 2. Here. The other one would be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here. So the green graph is the graph of x of omega. let's just write down x of omega. So this one shifted to the multiplied by 1/2 and move it to the right, and multiplied by 1/2 and move to the left, shift to the left. So the time scale would be omega 0 and minus omega 0. And this, of course, is t over 2. Okay, t over 2 here. All right. Okay. So the one in the center, the one in the center is what we are after. Okay, but then we know that we have to shift to the right and shift to the left, right? And take 1/2 of it. So that's why we have the green ones here. So the green ones are the spectrums of the pulse cosine, of the pulse cosine. Now the next one is exponential. Number 6. Decayed exponential. Decayed exponential, what I refer to is this signal x of t, which is e to the minus atut, where a is greater than 0. So if you try to plot this signal, you'll see that it would be the decayed exponential that starts from time 0. Okay, and it goes down, and it goes down here, and it would be 0 when time is less than 0. The maximum value is of course 1. This is what I mean by decayed exponential. So now let's try to find the Fourier transform. Let's try to find the spectrum of this one. In this case, we can use the direct integration to find the Fourier transform. It is pretty easy. So x of omega, which is the Fourier transform, the frequency spectrum of this decayed exponential. Now we use the definition of the Fourier transform. If you recall, it is the integral that extends from minus infinity to infinity. And then we plug in x of t, and in this case it is e to the minus atut. And then we multiply it by e to the minus j omega t, and then dt, because we're integrating with respect to t. So now we have to eliminate the function u, right? And we know u is 1 whenever t is greater than 0. So we have to change the lower boundary of the integration to 0. So the integration has to go from 0 to infinity, and then we can replace u with 1. But we don't have to write down 1, right? That would be redundant. So it would be e to the minus at, e to the minus j omega t dt. And then I know that I can group the exponentials together to get e to the minus a plus j omega, and then times t, and then dt. Okay, and now I can use calculus 1 to integrate it. So this would give me minus 1 over a plus j omega, and then e to the minus a plus j omega, and then plug in infinity, and then minus e to the 0. Now, because a is greater than 0, right? Because a is greater than 0, so this term will converge to 0. Okay, so this term converges to 0. And this term is of course 1. So we are left with 1 over a plus j omega. And this is the spectrum of the decayed exponential. Okay. So if we try to take the magnitude of this, the magnitude of this spectrum, because now if you look at this one, this is a complex number, right? There is a term j here, so it is a complex number. So if you try to plot it, you cannot do that. So if you want to plot it, you have to plot instead the magnitude and the phase. So let's find the magnitude of this. The magnitude of this is just 1 over the magnitude of a plus j omega. Okay, this is from complex number. And the magnitude of a plus j omega is just the Pythagoras of a and omega, right? So it would be square root of a squared plus omega squared. So this is the magnitude of it. Now what about the phase? The phase of this spectrum would be the phase, would be the phase of 0 minus, the phase of 1, minus the phase of a plus j omega, right? Because we know that the argument of divisions, okay, I'm not sure if you remember this. If you try to find the phase of z1 over z2, the result would be the phase of z1 over the phase of z2. Okay, and the phase of z1 times z2 is just the phase of z1 plus the phase of z2. This is from complex numbers. I'm not sure if you remember this. But now, in this case, z1 is 1, right? So I'm writing down the phase of 1 minus the phase of the denominator, which is a plus j omega. So it is this guy. Now the phase of 1 is what? Anybody, can you answer me? What is the phase of the number 1? The phase of number 1 is just 0, right? Because it is a positive real number. A positive real number has a phase of 0. So this guy is 0. Okay, and what about this guy, the phase of a plus j omega? It is an arctangent of omega over a. So you got, you got equal to minus arctangent of omega over a. So let's try to plot this. So the left graph would be the magnitude of the spectrum. So we want to plot this guy, okay, on the left graph. And we have, if you try to plot it, you have this graph here, okay, and this is 1 over a. And as for the phase, it's just the phase is just minus arctangent of omega over a. So if you plot it, you would have this graph. Sorry. You'd have this graph. And it has to be pi over 2 and minus pi over 2. Okay, this is 0. And this is the phase of x, the phase of the spectrum. Okay? You see, when omega is infinity, right? When omega is infinity, arctangent would be pi over 2. But you have minus the negative sign here, so it has to be minus pi over 2 when omega approaches infinity. But when omega approaches minus infinity, the arctangent would be minus pi over 2. So if you multiply by minus sign here, you're going to get positive pi over 2. So you have this graph, right? What is the time here? All right, we have a lot of time left. Okay, are you with me? Are you guys with me? Is it going too fast? I hope not. If it's going too fast, please let me know. The next thing I'd like to discuss is how about periodic signals. The thing that makes uh, if you try to find the Fourier transform of a periodic signal, then it is going to be pretty difficult. The reason why it is difficult is because periodic signal doesn't converge to zero. Okay, and because periodic signals do not converge to zero, the Fourier transform integral will not exist. Okay, it doesn't converge to zero as well. That's why trying to find the Fourier transform of periodic signals becomes pretty complicated. But we can we have a go around. Okay, we can overcome that difficulty by with the help of delta signal. Okay, the delta signal is just like a savior for us that that lets us uh, find the integral of something that doesn't converge to that is not finite. So we will usually resort to delta functions. So now let's try to find the Fourier transform periodic signals. Now, if you recall, whenever I talk about periodic signals uh, in homeworks or in exams, I always start with this form. Okay, you remember this form? G is a generating signal, right? For example, if G is this signal, if G is this signal, then X would be G placed every T0. Okay, so X would be this, this, and go on, this, and go on. This is going to be X. I'm not sure. I really hope that you can recall this. Okay, you recall this one? So this is how we write down periodic signals in as a repetition of the function g. G is a finite support signal. You remember support of a signal in the very first lecture? And so because g of t minus nt0 can be written as g of t convolved with delta t minus nt0. Do you see this? You see this, right? If I didn't have nt0 here, that would be very easy, right? Because delta is the identity of convolution. So, but when we have to shift delta to the position nt0, it means that I have to shift the whole thing, gt to nt0 as well. So that's why we have this signal. So plug it in, we have x of t equal to infinite sum that goes from minus infinity to infinity, g of t convolution convolved with delta t minus nt0. And because convolution integral is a linear operator, I can take g of t out of the series, or out of a summation. So we have g of t convolved with infinite summation goes from minus infinity to infinity delta t minus nt0. This equation comes from distribution property of convolution. Distributive. Distributive property of convolution. I am writing down star as convolution because I don't want to write down the whole convolution word. And now we are in a position to take the Fourier transform of both sides. So if you take the Fourier transform of both sides, the left-hand side would be the spectrum that we are after, okay, which is x of omega, which is the spectrum of the periodic signal. And the right-hand side, now it is if you remember, well, let me write it down first. The right-hand side is just the Fourier transform of convolution. And we know the Fourier transform of convolution is the product of the Fourier transform. Remember? Convolution and product, they go together. If one is convolution, the other will be the product. So if the time domain is convolution, the frequency domain will be the product. So this is the Fourier transform of convolution. So the result will be the product of the Fourier transforms. So it would be the Fourier transform of G, which is denoted by capital G of omega. And the other would be the Fourier transform of summation n goes from minus infinity to infinity delta t minus n t 0. Now here comes the most difficult thing. Okay, we have to determine what this guy is. Now there are two possibilities to do it. There are two ways to do it. The first way is to take the Fourier transform operator inside of a series. Now if you do that, if you take the Fourier transform operator inside a series, you're going to end up with Fourier transform of delta. And this will give you the complex exponential, and you'll be left with the infinite sum of the complex exponential, which leads you to nowhere. So if you attempt to push the Fourier transform inside of the series, you would be stuck, you would go nowhere. So the first method is not viable. So we have to think of another method to find this Fourier transform. Now, if you look at this closely, you'll see that this is just another periodic signal. This is periodic signal, right? This is a periodic signal, and if you recall, it is called the impulse train. This is an impulse train where you have impulses at every t0. Okay, every t0 you have an impulse coming up. Every t0 you have an impulse coming up. So you have an impulse train, right? Now, so this is a periodic. So it has Fourier series. The Fourier series of it is, if you recall, if you go to chapter 3, the Fourier series is just summation goes from k minus infinity to infinity 1 over t0 e to the j k omega 0 t. So this is the Fourier series of the impulse train. If you don't believe me, you can go back to chapter 3 to find it. So I plug in the Fourier series here into the Fourier transform. So I'm going to have g of omega, Fourier transform of summation going from minus infinity to infinity 1 over t0 e to the j k omega 0 t here. Okay, what I did was just I replaced this impulse train with its Fourier series. Okay, I'm replacing the Fourier series to the impulse train here. So I got this one. Now I can take the Fourier operator inside of the series. So I'm going to have g of omega and then 1 over t0. And then the Fourier summation k going from minus infinity to infinity. And then Fourier transform of e to the j k omega 0 t. Now, I can use the a property of a Fourier transform. This is a complex exponential property. So I know that every time I multiply a signal with the complex exponential, I'm shifting the frequency of that signal by this amount. So the Fourier transform of this guy would be delta, because the Fourier transform of 1 is delta, but now delta shifted by the frequency k omega 0. So this would be omega minus k omega 0. Okay, this comes from Fourier transform of 1. Actually, we have 2 pi. Fourier transform of 1 is 2 pi delta, right? Fourier transform of 1 is 2 pi delta, but now we don't have 1, but we instead multiply 1 with complex exponential. So every time we multiply by a complex exponential, that's a property, right? We're going to have to shift the spectrum by this amount. That's why we have this. That's why we have this. You see that? So we have this. And so we have we have 2 pi over t0 g of omega and summation from k equal to minus infinity to infinity delta omega minus k omega 0. And we realize, of course, that 2 pi over t0 is just omega 0. So we have summation k goes from minus infinity to infinity and omega 0 g of g of k omega 0 delta omega minus k omega 0 here. And this is the spectrum of the periodic signal that we are after. Ah. What I've been doing is I've been trying to come up with this formula here. Okay, so let's look at an example. Let's try to find the Fourier series. Let's try to find the frequency spectrum of a rectangular pulse train. Rectangular pulse train is a pulse train of rectangular. Sorry. So rectangular pulse train looks like this. You have a kind of a rectangular pulses, and you put it every t0. And then blah 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 and blah blah blah. okay, to tell us that it goes on forever to the right and to the left. Doesn't stop. So this is a rectangular pulse train. Um, the period is t0. The magnitude is a. Let's call it a. And the width of each pulse, the width of each pulse is t. Is big T. Now this is a periodic signal, of course. So we would like to find the Fourier series. I'm sorry, the Fourier transform of it. So the first thing to do is to find the generating pulse, right? The generating pulse is a pulse of one period. So it is defined by this signal. This is the generating pulse. Because you see, the x of t, the signal x is this signal is this pulse placed every t0. So this is the generating pulse. So what is this pulse? This is a rectangular pulse, right? So I'm gonna highlight this and say that this is a generating pulse. Yeah. This is the generating pulse, and this is GT. Okay, because we're putting GT every T0 time units. So GT is given by A times rectangular T over big T, because the pulse, the width is T, right? The width is big T and the height is A. So this is a rectangular pulse. Now to find from this formula, from the formula above, we have to find the Fourier transform of the generating pulse, right? And replace omega with k omega 0. So because the generating pulse is a rectangular pulse, that means that g of omega, which is the spectrum of it, is a t sinc function omega t over 2. So this is the Fourier transform of each pulse. And then I have to plug it into this summation, right, to this formula. So I have x of omega equal to summation k goes from minus infinity to infinity, 2 pi over t0, g of g of k omega 0. So that is a t sinc of k omega 0 t over 2, and then delta omega minus k omega 0. Here, this guy, okay, this guy, the thing here comes from replacing omega here with k omega 0. Okay, I have to replace omega with k omega 0 because actually we have this, but we know that we multiply this with delta. So when we multiply something with delta, we just replace the variable here with k omega 0, because delta is nothing except at k omega 0. Everywhere else it's 0. So we have this one. So we have this. And then I have um, 2 pi a t over t0 summation of k going from minus infinity to infinity sinc function of k omega 0 t over 2 delta omega minus k omega 0. So this is the frequency spectrum of a rectangular pulse signal. So let's try to plot this one. The graph of this is pretty easy because it is all real numbers. There are no j terms here, so you don't have to take magnitude and phases. So this is pretty easy to plot. So let's try to plot it with respect to omega, of course. Now, when every time you plot a sinc signal, you have to be able to locate the zero crossings. In this case, the zero crossing is given by, you may view this as omega here. Okay, so the zero crossing is given by omega equal to 2 pi over t. 2 pi over t are the zero crossings. So the first zero crossing occurs at 2 pi over t0. I'm sorry, 2 pi over t. The second occurs at 4 pi over t. The third occurs at 6 pi over t, and so on. And on the left is minus 2 pi over t, minus 4 pi over t, minus 6 pi over t. These are the zero crossings of the sync signal. And then we'd have to draw the sync signal itself. So it would be this. Yeah, this is a sync signal. This is 2 pi at over t0 sync omega t over 2. Here, this one. And then I have to multiply by delta that occurs every omega 0. So the delta, the height of the delta is controlled by this envelope, right? This envelope controls the height of delta. So I have to place delta here, every omega 0. So I have this, the first one, the second one, the third one, the fourth one, and so on. Okay, the impulses are every omega 0 apart. So I have this. This is omega 0. Or 2 pi over t0. And t0 is greater than t, so omega 0 is less than 2 pi over t, which is the zero crossing. Okay? So this is the frequency spectrum of a rectangular pulse signal. Of course, if you change a generating signal, in this case, in this example, the generating signal is a very easy signal. It is a rectangular signal, right? But if you change it, if you can change it to everything that you want, right? You just have to take the Fourier transform of each pulse, and that would be your G. Okay, it could be a triangular shape signal. It could be a sinusoidal signal. It could be everything that you want. Okay, you just have to be able to take the Fourier transform of it, and the periodic part is just multiplying it with the delta at every omega 0. So next time we'll be talking about energy density spectral. Okay, I'm gonna give some introduction to it. In this topic, there is a theorem called Parseval theorem. Parseval theorem states that if you want to integrate the time signal, the magnitude of the time signal squared, okay, if you integrate it with respect to time across all the time, the result from the integration would be the same as if you are integrating the frequency signal across all the frequency spectrum. But you have to square it first. This is called the Parseval theorem. It is a very important theorem down the history. So I'm just going to highlight it. This is important. This is called Parseval theorem. The reason I'm putting the absolute values here, the absolute signs here, is because I have to be aware. I have to be careful because if x is a complex function, then I cannot just square it. I have to square the magnitude of it. Okay, so that's why we have to have absolute signs there to take care of the in the complex number case, complex function case, and you have to be careful not to forget about the factor 1 over 2 pi here, and you have to be careful that the integrals would have to extend from minus infinity to infinity in both domains. And we realize that the left hand side is what? The left hand side is the energy, right? The left hand side is the energy. So from Parseval theorem, we see that energy of xt can be found both in the time domain and in the frequency domain. So it is equal to integrating from minus infinity to infinity absolute value magnitude of xt squared dt. This is in time domain. Okay, we are finding if you try to find the energy using this integral, then we are trying to find it in the time domain using the time domain signal, or we can find it using the spectrum of it. So it is the area under x of omega, the magnitude of spectrum squared d omega. Actually, this has to be d omega. Sorry about that. This is changed to be d omega. Okay. So this is d omega, and this is in the frequency domain approach. And they turn out to be equal. Okay, they turn out to be equal. All right, so I'm gonna leave it right here for today, and we're gonna resume on Thursday. All right, we're gonna resume on Thursday. Should we check attendance today? Should we? Because a lot of you guys cannot attend. Should we check attendance? All right. What do you say?